Now that we understand that we can take either a backward or forward stepwise procedure to add or remove variables, we need to figure out what our criteria are going to be. And we kind of have a trade-off to make here. We want to reduce the number of explanatory variables that we have in the model, but at the same time, we want to increase the goodness of fit, obviously. So the more variables that we add, that's going to inherently describe the data better, and it's going to predict the response variable better. So we have to figure out a way to discount that to a certain extent. We want to build a model that's simple enough to be interpretable and have the fewest amount of variables while still having the best model fit. So the first criteria that we can start off with is the adjusted R-squared value. And the reason that we call it adjusted is because it is accounting for or discounting based on the number of variables that we have. And so you can see that what's key here is that we, again, are looking at the residual sum of squares. So this is the unexplained variance, right? Because again, what this R-squared value is telling us how much our model is explaining. So that's why we're doing 1 minus that. And then this factor here is taking into account the number of variables. So that's what K is. And just with normal R-squared values, we also prefer a model that has a higher adjusted R-squared value. And you'll generally find that when you have few variables, the adjusted R-squared value and the R-squared value should be pretty much the exact same. And that is because this discount is essentially non-existent, right? The difference between the two is almost nothing. We could also use the cross-validation criterion, and this essentially is just saying that we are interested in seeing how far away our prediction is of an observation when we don't include that observation in our model. So this really is trying to say that if you use a lot of parameters, you're going to tend to overfit the data, right? You're going to really explain the data that you have very well, but it may not do very well at predicting a new observation that wasn't in the original data set that was used to fit the model. And so this is a really good criteria if we're interested in seeing how well our model does at predicting observations outside of the sample that's used to fit the model. Since this cross-validation criterion is distinguishing how good our model is at predicting an observation out of sample, we want a model that has a small CV, right? We want the distance between that prediction and what it actually is to be quite small, because that means our model is doing a good job at predicting out-of-sample observations. The second set of measures that we have are the AIC and the BIC. So first, the AIC is dependent on our estimate for the standard deviation within the sample. And we prefer a model with a small AIC. So this is really dependent on, one, the number of observations that we have, n, the observed estimated variance that we have, so sigma squared, as well as the number of parameters, k. Now, the BIC does discount more extremely for higher values of k. And this is the crucial part here. So typically, a BIC will be higher if you have higher numbers of covariates, all else equal. And we would interpret the BIC the exact same way, in the sense that we would prefer to have a small BIC. So for both the AIC and the BIC, more parameters will provide smaller sigma squared. But the second term adds on a penalty related to the number of parameters in the model. Now, it just does it more extremely with the BIC because we're multiplying it by log n instead of 2. And typically what we're going to do is use backward or forward stepwise deletion or addition using AIC or BIC as the criterion with which we will add or remove variables. And we'll walk through an example in the next